book, I tell you what. All right, so just at the top, I just reiterated the definition, okay, that in order to be continuous, the limit has to exist, the function value has to exist at C, limit has to exist at C, function value has to exist at C, and they have to be equal. And then, of course, obviously, just coming off of limits, the only way the limit is going to exist at C is if it's the same approaching from the left as approaching from the right. So this kind of has, like, prior to even getting here, you want to make sure the limit as you approach C from the left equals the limit as you approach C from the right. Question? If and only if. If and only if. Have you ever heard that phrasing before? If and only if? Yes? Oh, IFF is if and only if. Okay. So we know the phrasing. It's just, yeah, that's a short. I don't know if that's like a legit thing or if that's just what my college professors did. But it's also like the double-sided arrow. Did you ever do that? Yeah, it's a little bit different because you guys don't do any logic really anymore. But like, you don't know like how to read that. If P, then Q. Because you guys have never done logic. You've done proofs in geometry, but you used to do logic, where you learned a little bit about that logic notation. But we won't get into that. So maybe the double-sided arrow means nothing to you. But anyway, so there's your definition reviewed. A removable discontinuity, we've talked about it as well. So a removable discontinuity at a certain location C exists if the function can be made continuous simply by redefining that f of C value. So that's where visually, if you look at it, if you could put in 1 point, would it change the graph into being continuous? And if the answer is yes, if you could do that, that is considered a removable discontinuity. But other ones that are non-removable would be like asymptote discontinuities, jump function discontinuities, piecewise discontinuities that are separated by a jump, all that good stuff. So, okay. So, we're back to some basic limit stuff. This is just a jump function that's been shifted 10 units to the right. So there's definitely a jump at 10. So the overall limit we know will not exist. But if you're approaching 10 from the right, Nate, what would the limit be? 1. If you're coming from the right. Very good. Positive over positive would be a positive 1. On the second exercise, remember, we know that this is a little bit of them kind of getting at the f of x plus h derivative stuff, but pretending we don't know that, if we're approaching 0 from the right, so first of all, given that it's from the right, something funny is probably happening at 0. If you plug in 0, you're going to get 0 over 0, so we need to manipulate. So I'm going to square this out. Carrying down my limit. I'm going to cheat. So my limit of this, the x squared minus x squared will cancel. The plus x minus x will cancel. And we'll have the change of x squared plus 3 changes in x. All over changing in x. And I'm going to cheat because this is going to continue to come down, this limit written out in front. And then it's going to simplify, and so it's going to be the limit as the change of x approaches 0 from the right, and both of those terms are divisible by change in x, so it's change in x plus 3. And actually, once you simplify, you now realize it doesn't really matter if we're coming from the left or from the right. Can we all agree on that? Okay? Because once it simplifies, 0 is not still an asymptote. 0 is not still a place of interest because that 0 denominator just canceled out completely. So we just had, like, really this boils down to a linear function that had a hole. So you plug in 0 and you get 0 plus 3 is 3. Just because we do know the f of x plus h minus f of x issue, what was this function? What is this function that they're finding the limit of, or really technically they're following the derivative definition by doing limit as it approaches 0 f of x plus h? What is the function for which this is finding the limit? What do you think, Mitch? Right, x squared plus x. And you can see that because here's the, think of it as x plus h for me for a minute. Here's the x plus h squared plus the x plus h minus the plain old f of x. So what they're doing is they're really figuring out really what the derivative of this is as the change of x approaches 0. Joey? I see your hand going up. I was just going to say that's not the derivative. The derivative shouldn't be 3, so what did I do wrong? And you just found it. So when I squared this out, I screwed this up. It's x squared plus 2x change in x. When I FOIL, my outer is going to be x change x, my inner, so it's 2x change in x. Which means this is not combinable. 2x change in x plus change in x. Of course, it's going to trickle through the whole problem. Oops. Oh yeah, that's right. Change of x approaching 0. So each one of the 3 of these, the change in x can cancel out. So it's going to be the change in x plus 2x plus 1. And now, as the limit of change in x is approaching 0, still from the right versus from the left does not matter. And you plug in 0, and this ends up just being 2x plus 1 is your answer, which is the derivative of the f of x function that Mitch identified. Okay? With h's, it's so much easier. The change in x throws such a wrench into it. So for these, if you want to change all your change in x's to h's momentarily, just to keep it clearer, you're definitely welcome to do that. But again, the textbook doesn't think we know anything about derivatives right now, but we do. And what we just calculated was the limit as h approaches 0. Who cares? It didn't matter from right or from left in this particular case. So we actually just calculated the derivative. Okie doke? All right. So limit of the secant graph as you approach pi over 2. So whenever I see like a trig graph like that, I don't know secant values off the top of my head. But I do know that it's 1 over cosine if I want to change it to that. And what is the cosine of pi over 2? If I directly evaluate? Cosine of pi over 2 is 0. 1 over 0 is undefined. Now, because we do know the nature of secant graphs, this is undefined due to an asymptote. Yes? So if this was asking for the limit as you approach from the left or from the right, we'd have to search further. But because you should have at least a minimal understanding of the secant graph being the reciprocal of the cosine graph. So we draw in those asymptotes and we flip things over. Trying to do my secant graph a little more boldface. Just because we should know the nature of a secant graph, we know that they're not the same behavior on both sides of the asymptote. So that limit being able to be written any more specifically than does not exist would only be possible if they were asking from a certain side. Any questions on that? And then one more, we have a step function here, that notation. And step functions change from step to step at different, usually integers, although they could write it so it didn't. So you just want to kind of wrap your head around what's happening surrounding 2. Okay? So, and we're approaching, and 2 is likely going to be the end of a step, which is why they're asking for it coming from a certain direction. Do we follow that? So just look at what happens to the right of 2. Like if you plugged in 2.1, you would get, so if I'm plugging in 2.1, I'm going to get 2 times 2.1, which is 4.2, minus, what is the greatest integer less than or equal to 2.1? 2. So this would be 4.2 minus 2, which is 2.2. What if I plug in 2.01? That'll be 4.02 minus the greatest integer function. What's the greatest integer less than or equal to 2.01? Still 2. So as we get closer and closer to 2, it's not ever going to be changing this. It's just making this one closer and closer to what? This first section, 2x, is getting closer and closer to 4. And you're always going to be subtracting 2 from it, so the overall is going to get closer and closer to 2. And you can see that progression slightly starting, 2.2, 2.02. And if you really wanted to be annoying, you could do 2.00001. So 2 times that would be 4.00002 minus the greatest integer less than or equal to 2.00001 would still be subtracting 2 off of that. So it would be 2.00002. So as we're approaching 2 from the right, the overall value of this is approaching 2. Yes? Okay? I just want you to think back to that property that says if you're finding the limit of some function minus another function, you can find their limits separately and subtract them from each other. Right? That property? The limit of 2 functions being subtracted can be calculated by finding the limit of the first minus the limit of the second. Yes? So if we wanted to look at this one that way, this would be finding the limit of 2x as x approaches 2 from the right, and also finding the limit of the greatest integer function as we approach 2 from the right. Now, on the linear part, the from the right or from the left doesn't matter. Agreed? Just plug in 2 and you get 4. Minus, on the greatest integer function, if you're approaching 2 from the right, let's say you plug in a 2.1, a 2.01, a 2.001, this whole thing is still always going to be 2. Agreed? Yes? 4 minus 2 is 2. So you can do it, separate it kind of into a linear and a step function if you'd like. Okay, so again, just looking more at these tricky examples. Natural logs. So this is the natural log of 6 minus x. What is the domain of this graph? You're only allowed to take the natural log of what? What kind of numbers? Positive. So 6 minus x has to be positive. So if you add x over, 6 has to be greater than x. In other words, x has to be less than 6. So if you were sketching this log graph, there's an asymptote at 6, and the graph only exists to the left of it. Another way we can think about this graph is if you rewrite it as the natural log of negative x plus 6, right? This is technically the natural log of negative 1 x minus 6. So we flip it horizontally. So if you think about the parent graph, which would look like this, you flip it horizontally and then move it 6 units to the right. Does everybody see that? There's the horizontal flip because it's a negation within the function, and then here's the shift 6 units right. So there's your parent graph of a natural log. Flipped over would throw it there, and then 6 units to the right would bring it right here. So now you have an idea what the graph looks like. So if you're approaching 6 from the left, where's this graph headed? Negative infinity. Now that, I just did that graphically. If I thought about it numerically, if I plugged in something slightly to the left conceptually, 5.99999, right? What's going to happen to 6.5999999? Teeny tiny. The natural log of something tiny, a tiny positive, by the way. If you were asked that question, you would think of just the regular natural log graph, because at this point, this is where we would be. The negative, or the actual natural log graph, as you take the natural log of a teeny tiny number, negative infinity. Yes? So there's 2 ways to do it, and I think I noticed on the quiz yesterday that there was a little confusion, like people were doing some of the right things, but there was a confusion as to what graph at different times we should be looking at. Like, if I'm looking at the overall graph just by transformations, okay, now if I'm looking at the overall graph, I'm focusing in on what's happening as we approach 6 from the left. But if I've already done some calculations in my head and it boils down to the natural log of a tiny number, I need to be considering the natural log graph, not still considering the natural log of 6 minus x. Any questions on that? Okay. Here we have a natural log graph, yuck, mixed with a radical graph. Okay, so we're looking at approaching 5 from the right. So 5. Why is 5 a point of interest? Well, it might not be. Could I just directly evaluate for the limit at 5? Let's think, what is our domain? Because I do want to be careful if this graph just stops somewhere, right? So on the one hand, your denominator can't be 0, right? So x cannot be 4. On the other hand, x has, and all of these things have to be true, x minus 4 has to be positive because it's under a radical. Yes? And that would make add 4, x actually has to be greater than 4, for sure. So we don't really, this is redundant. If x has to be greater than 4, then it already cannot equal 4. So we definitely have to be greater than 4. We're also limited, though, because this whole thing has to be positive, right? It has to be greater than 0. Now, your denominator is always going to be greater than 0. Agreed? So we just need to ensure that our numerator stays greater than 0, which would just be an x is greater than 0, which is, again, redundant and unnecessary, because if x has to be greater than 4, then this one already had to be true, and so does this one. You want to look at all those things in case they're like kind of pointing in different directions. You want to make sure they're all true. But those other ones were included in the x is greater than 4. So this graph only exists to the right of 4. And there's no discontinuities when you're greater than 4. Right? So why would they be saying 5 from the right? I'm not really sure. I'm pretty sure the limit is going to exist. We'll look at this graph when I'm done figuring this out. But as you're approaching 5, 5 shouldn't create any sort of weird situation. Doesn't seem to be an asymptote. If I just plug it in and do a direct evaluation, it's the natural log of 5 over 1, which is the natural log of 5, and that's your answer. The limit of this as x approaches 5, it seems to me, whether it's from the right or from the left, it would still be that value. Stranger things have happened. Wrap your head around these. So let's look at it. Natural log. So Morgan, what's the consensus? Is this an easy day? It is? Oh, I think it's more the brain teaser ones, but all right, well, that's good. Let's see, Zoom 6. There we are. So we see that with our domain thought process, we were correct. X is definitely greater than 4. And if, like, I thought it was continuous at 5, certainly the limit is existing, so I do know that. I mean, I'm pretty sure the graph is not undefined there. I just plugged in 5, and I didn't seem to have a problem. Second trace value, if you plug in what's happening at 5, you get this weird 1.609 number, which I'm guessing is what the ln of 5 equals, 1.609. Okie doke? Okay, a lot of logic goes into that. Not a whole ton of written work, but a lot of brain exercises. All right. Yes. Yeah. Yeah. Because it's hard to, you'd almost like show your work via an explanation maybe, or just sometimes like when I do that, like I would consider that showing your thought process, somehow communicating what your thought process was. Yeah. All right, so a function is continuous on a closed interval from A to B. If and only if the function is continuous on the open interval, so in other words, in between, and if your limit as you approach A from the right equals the function value of A, and the limit as you approach B from the left equals the function value of B. So we're just looking now, rather than talking about overall functions, we're going to talk about certain little sections of functions. Is this function continuous, between these two numbers? So like if I took something, and I'll just give you an example. If this is A and this is B, okay? And we'll go through the 3 stipulations. Is this function continuous between A and B? Yes, right? Is the limit as I approach A from the right equal to f of A? Yes? Okay. And is the limit as I approach B from the left-hand side equal to f of B? Yes. So let me ask you this question. So we would be able to say that this is continuous on the closed interval from A to B. If I asked you this separate question though, Is it continuous at A? What would you say? No. Just at A alone? No. Because there is no limit at A. There's only a one-sided limit at A. Is there a limit at B? No. Because it's only one-sided. But this is just pretty much pointing out that we're still allowed to say that the function is continuous on a closed interval, and they will use brackets there. And really that does not actually mean it's continuous at point A. It really just means from A to B. Anyway, we don't need to get hung up on notation. We'll just carry past that. Might seem obvious. Discuss the continuity of these. So, and from -3 to 3. So, I think the first thing we want to do is maybe explore what this graph's domain is, right? So what do you know about 9 minus t squared? Has to be what? Has to be what? Greater than 0. And this is a quadratic inequality, so when you square root both sides, that doesn't mean... Wait, what did you say, Olivia? Or equal to, though. Or equal to. Sorry, I didn't pick up on that when you first said it. It doesn't mean that t equals 3 or -3, but it gives us points on number lines to check. So 3 and -3. Yes, it can equal -3 and it can equal +3 because it's not like it's in a denominator. But where is it that the points work? If you plug in a 4, is that okay? No, because it'll produce 9 minus 16, a negative number under a radical. Same thing with -4. So this graph actually only even exists in between -3 and 3. And so is it continuous on this closed interval? Any other reasons that it might be discontinuous in between -3 and 3? Is it a jump function of any sort? Greatest integer function, piecewise, or jump functions themselves actually create jumps. We don't have any of that. We don't have any denominators to dance around. So this is continuous on closed interval. -3 to 3. You want to see this crazy beast? I do. I probably haven't seen my old friend since last year. There we go. That's all it is. It's like a half circle almost. Okie doke. All right. This particular graph, x squared minus 4 just can't be 0, right? Agreed? So x squared minus 4 cannot equal 0, which means x squared cannot equal 4, and x cannot equal plus or minus 2. So the graph exists everywhere but plus or minus 2. I mean, this is a pretty easy one for us, or should be pretty easy for us to sketch a vertical asymptote at -2, vertical asymptote at +2. Our y-intercept when x is 0, if I plugged in the 0, I'd get -1/4. If I plugged in a +1, I would get a -1/3. If I plugged in a -1, I'd get a -1/3. So do you see how that's turning around? Yes? Think about it. Getting infinitely close to 2, like 1.99999. that's going to put something infinitely close to 4, but on the underside of it, right? Like 3.99999. And then 3.99999 minus 4 is a teeny tiny negative number. 1 divided by a teeny tiny negative is negative infinity. And then because the degree of our asymptotes is odd, it's just going to have opposite behavior on the other sides. You might also notice this is an even function, so it should be symmetrical to the y-axis. You might also think about horizontal asymptotes. Small over big means there's a horizontal asymptote at 0. So is this thing continuous from negative 1, which is here, all the way to 2? So let's go here. Is it continuous between negative 1 and 2? Yes. Is the limit as you approach A from the right, which is the negative 1, as I approach negative 1 from the right, is the limit of that equal to the function value there? Yes. And as I approach B from the left, which is 2, as I approach that from the left, is the limit there equal to the function value there? No. Because the limit as I approach there doesn't exist, number one, it's negative infinity. And also the function value at 2 doesn't exist. So that's not true for this particular problem. And so this is not continuous on the closed interval negative 1 to 2. Yep. Yep. It's an automatic write-off. Yep. So you'll see a little bit more about open intervals versus closed intervals and so forth. But in order to be considered continuous on the closed interval, essentially both endpoints have to exist, and it has to be continuous in between. So you're drawing a continuous, smooth, anything in between. Okay? Now it doesn't have to be smooth. It just has to be continuous. That's the short of it. Now when you're boiling down definitions, that's the definition. And sometimes those multiple choices are written so that we have to do that.